Today, our speaker is Zhenyu Zhao from Tencent. So Tencent is actually like a mirror of a company from Silicon Valley in China. So it has like a lot of products. Like one of maybe the well-known is like the WeChat, which is kind of like WhatsApp plus Venmo plus many more. And then actually Tencent has like a large share in the global game industry. And if you play like say Fortnite or Leagues of Legends, and Tencent owns a part of that. Okay, the investing part of that, and many more. So today we are going to have Zhenyu, who is the data science director at Tencent for Global Games, to talk about from experimentation to causal learning, so that we can see, how data science is used in real applications. Zhenyu got his PhD in Stat from Northwestern, and he has experience in Uber and Yahoo before joining Tencent. And his research expertise covers experimentation, causal inference modeling, product analytics, and data platform solutions. So without much more introduction, so let's welcome Zhenyu.
All right, so yes, thank you for giving me this opportunity to share some stories and methods we used in industry with the audience. And so in this presentation, I'm going to share some case studies, some methods, some challenges we see in the industry from experimentation to causal learning. Since this area is probably one of the data science field areas that are very correlated with statistics community. So hopefully we can find something interesting in this topic. So the goal of this presentation is to give us a broad idea of different methods, use cases we see. So probably we are not going to too deep into one area, just to save time for broad coverage. Okay, so in this talk, I'm going to first introduce what is A/B testing, what is the concept of this mostly commonly used experimentation method in industry. And then we will share some concrete examples just to give us some ideas what it actually looks like and what values it can contribute to the business. And then we are going to talk about definitely statistics behind experimentation. Why, in the experimentation team, we always prefer to have some statistician on the team. And then we are going to talk about from engineering perspective, how it actually functions, how it actually works by connecting different dots in the system. And then we are going to go beyond A/B testing. We are going to talk about general methods in the experimentation and causal inference field we see valuable in applications in industry. And then in the end, we are going to get on another topic, which is CausalML. This is open source Python package for causal learning. I'm going to give intro to this package, and hopefully, we can also, have some usage of this package in the future. All right. So first, what is A/B testing? So here is one simple demo example. So we have two versions of mobile product. So one layout looks like version A, and another layout look like version B. So maybe both design have their logic. So have their, why this is a better design from the design theory. However, we are not sure which version we should launch to all users. So we want to have a better version in terms of user engagement. We hope our users like the version we launched. So then how to make a decision? So if we are the CEO of a company, how can we make a choice between these two versions? So this is a decision question. So whenever we are making this type of decision, we don't have enough information. We don't know actually, because our user group are so large, we don't know everyone how they think about the designs, which version they prefer. But most of our case, we make based on our decision, based on previous experience. So which is not sufficient. We don't have sufficient information or data from our user. So the ideal solution is a parallel universe. So assuming we have two parallel universe, everything is the same, except this product's version is different. So in the first universe, we launch the version A of the product. In the second universe, we launch the version B of the product. Then we can observe in these two universes after 1 week, which version of the product get more popularity. So that's and then we can do a time travel back to the time point before launch, and then we make the right decision. However, this in the ideal world. In reality, we can use A/B testing to mimic parallel universe. So basically, we just divide user into two groups and just assume they are coming from two parallel universe. So that's the concept of A/B testing. And the flow of A/B testing is pretty simple in concept. So we have a user group of our product, and then we divide them randomly into control and treatment. And then for control users, we will let them see the version A, and for treatment user, we let them to see version B. And then after 1 week, we will just conduct analysis and see which version of the product user like better. So how to measure their preferences. Normally, we will measure their number of active days for the product, their user retentions, their time spent on the app, maybe also involve some like number of items they purchased or number of videos they viewed, or number of items or articles they browsed. So basically their engagement with the app. And then we compare their metrics. So for example, after collecting the data, if we see version B has a better engagement, then we will launch version B. Otherwise, we will launch version A. So given the data on hand, we are able to make a more data-informed decision. So this is a basic flow, very simple. Now let's get into some real examples. So the previous one is just a dummy example. So what's actual A/B testing example look like in industry? What's the problem we solve? So here is one example from Microsoft Bing. This is also kind of a famous example. So first of all, let's see whether we can tell a difference. So on the left, this is a control experience. That's a default experience on a search page. And on the right, this is a treatment page. So this is a new page design. But first of all, let's take a look on these two pages and see whether we can actually tell the difference, which part the product got changed from control to treatment. So let's pause for 5 seconds. All right, so actually the change is pretty minor. So basically they change the color shade. So for example, for the blue link, they change from light blue to dark blue. And for the background, they change from this type of green to this type of green. And for the description, they change from dark black to gray. So that's a very minor change. So, but why do we actually want to run this type of experiment in industry? This is just a very minor change. So the background is that in 2013, Microsoft Bing runs a series of experiments for font color on search result page. And they tested multiple treatment and multiple color design. And the treatment we show on the right is actually the winner. So this actually improves the time from search to click, their core metric, and also leads to a revenue increase over $10 million per year. So first of all, why do we see a big change revenue increase because of this small change? The reason is because for internet product, there's a huge number of users. And if we can increase the revenue by 1% or even probably 0.5% or 0.3%, that's a large amount of money. That's a effort is worth doing. So that's why such a small change, as long as it increase the revenue, increase the click-through rate a little bit, then it will actually increase the total volume of revenue significantly. So that's the beauty of experiment. So it actually can help us to navigate which design is slightly better than the other, and such that it can lead to a total amount of gain, which is quite significant. However, we may question, okay, so we tested probably 10 or 100 different designs, then maybe just one treatment randomly stand out is just probably by noise. We know there can be false positive, whether it's a case. So the team actually repeat the experiment for a larger population to confirm it's not due to random, and their findings for the conforming experiment are consistent with their previous findings. So this color coding is indeed better than the previous one. So maybe majority of users cannot tell the difference, but some user on some desktop, on some devices, on some certain browsers, they may have a slight difference. And similarly, this type of experiment is not only done at Bing. Google also tested 50 shades of blue, and they claim that so this type of change in color in Gmail and search give their company an actual $200 million a year in revenue. So from this example, just want to tell us, in A/B testing, many times we just test some small changes, but these small changes actually matter. Okay, here is a second example. So this example from Netflix, which is a online streaming company. So they have different video contents on their website for user to browse and choose which content they want to watch. And one time they tested different covers for video content. So for the same video content, which is a short game, they just have 3 different cover pages. And so if you are the user, which cover page seems more appealing to you, you are more likely to click and find out what the content is. So let's also pause for 5 seconds and let's make a choice. So which cover looks more attractive to you? Okay, so actually, the winner color is the second one. So the first one is the control experience, which is the default online experience. And the second one lead to 14% relatively increase in conversion rate compared to the first cover. And third one leads to 6% better conversion rate than the first one. So this example actually tells us the artwork, the cover can actually lead to a change. And this type of change the cover or change some picture, change some title. So these are widely applied in different A/B testing scenarios, including some video content. Also involve some scenarios in games. In games, we also sometimes have some campaigns. Or maybe we have some ads. Many ads also have a video or have a picture or have some text content. We can also change that. That can also lead to a significant difference in the end. And maybe you didn't choose cell 2. That's very normal. That means not every user have the same taste. To test that out, the Netflix team conducted a second experiment, which ran an experiment in different countries. They want to find out whether different countries have a different preference over different cover. So in the end, they found out in Germany, the first picture one in Germany, and the second picture one in Brazil, third picture one in US, and the fourth picture one in UK, and last 2 didn't one in any of the country. So this experiment actually told us users may have different preference in different countries, and to make it more broad, generally speaking, users may have different preference individually, and that's one topic we are going to cover in causal learning: how to detect the individual user's preference in an experiment. Okay, and the last experiment example is a kind of a legacy example. Is from 20 years ago, but the idea from this example is very important. So around 2003, so engineer at Amazon proposed an idea. So when user check out, so when user put one item into their shopping cart, should we recommend some relevant items for them to consider, just as this is called shopping cart recommendation system. And in this case, SVP, marketing SVP, just had some concern. So based on the past experience, we want to make the checkout flow as simple as possible, the shorter the better, to avoid distracting users and impacting the final purchase rate. Because maybe I plan to check out this item, but I was distracted for some other items. I just begin another browsing flow and forgetting about checking out the original item. That's possible. So due to this concern, the team didn't fully develop this feature, but Greg didn't give up. He developed MVP and carried out a small sample size experiment. And amazingly, the experiment results shows a very significant lift in the total revenue gain. And based on the experiment results, all teams get aligned and get on board on the idea. And right now we can see this shopping cart recommendation are applied in many e-commerce websites. So the takeaway from this example is that without experimentation, many times we need to base our decision on past experience or based on some logics or based on what our competitors do. But with the experiment, we can actually collect the real feedback from users. And with experiment results, the team are also able to get aligned faster, especially if this decision need to involve a lot of teams. Different teams have different opinions, have different experience, have different KPIs. Then the experiment is a way to make a very quick, efficient, and data-driven decision. So when it comes to games, where we can run experiments. So if we are talking about probably 20 years ago or even 10 years ago, many games are published through the hard copy selling, right? So we purchase a hard copy, probably a CD, and then we just install it on our PC, and then we begin to play game. And there's no update from the game company to my local offline game. So in that case, it's really hard to run experiment. But nowadays, we can see there are more and more online games. So like we download a game app. So it's not strange to see there's a lot of updates. So every 2 weeks or every 1 month, we may see an update to update the app. So whenever we update the app, there are some new features released. So there's a chance we can run A/B tests. So basically, we just test which feature is better, and then we will make that feature into the next release. Then, what concrete scenarios we can run A/B testing or experiment in game products? So basically, the use cases can be throughout the user lifecycle. So even before the user become a game user, we will run some campaigns like ads campaigns through Google, Facebook. Then for these campaigns, we need to first evaluate how does this campaign do it? Does it actually have a real impact on our user acquisition, or we have different plans, different strategies for the ads? For example, user targeting, ads content, bidding strategies. We can run experiments to compare different strategies. And when user come to the App Store to download the app, we can also test different app icon, different App Store screenshot content to give our users some idea what the in-app experience look like. So after user get into our app, download the app, and begin to register their sign-up interface, that's also super important because there can be a drop-out funnel between user install and actually play the game. So we also want to design the sample flow and register flow as simple as possible. And how to make the trade-off, we can run different experiments to compare different sample flows. And also when user begin to get familiar with the game, many times there's some new user guidance. There's a guide to get you, oh, here's a step. You need to probably, at this situation, you should shoot, and how to, use your skills, how to purchase the item. So those are the guiding information through the new user journey. But how to design the steps, how to make a trade-off between the information we provided, because if we design the new user guidance too long, then many users may get bored. If we design the new user onboarding process too short, then many users didn't get the game, so they didn't know, oh, what's actually the play mode of the game. So that's also not ideal. So we need to make a trade-off to make a the best choice that user get familiar with the game without getting bored. So that's where the experiment can play a role to find out the trade-off point. So whenever the user become our mature user, they open the gate for many play mode and many scenarios within the app. And for experimentation, we also have many applications there. So for P2P games, we can test different matching algorithm. We can also test different promotions and targeting tasks. So you may see some, like if you continue to log in 7 days, you will get 100 gold coins. Or maybe we make an experiment and say maybe you need to log in 7 days, and also maybe you also play a game at least 1 time a day, you will get 200 coins. So which one is better? We can make an experiment and do a comparison. We can also run some social experiment to say, oh, what is our social campaigns, our social friend recommendation algorithm does. And we can also run some item recommendation algorithm in the store. For push notification, we want to find the best frequency, best to push the right content to the right audience on the right time. And for this type of push strategy, we can also use experiment to find out the best strategy. And also sometimes there's a new game mode released. We can also, in the treatment, we can open the new game mode for the treatment user, and for the control user, they don't see the new game mode. We can also test what is kind of impact on user engagement with that new game mode. Definitely for user interface, we can see different icons, different layout, background image in the game. We can play a lot of experiment within the game in the user interface to see how we can design the icon, how we can design the navigation order. Whenever the mature user have the risk of getting churn, which means they are going to leave the game, or they already left the game, they haven't opened the game probably for 7 days or for 1 month, we can design some promotion offers to them, either through in-app channel or through some ads channel. So that's a kind of a brief overview of different use cases in game products where we can run experiments. Okay, next let's take a look on what the industry experts say about experimentation, why we find experimentation as a valuable methods and tool for tech industry. So Jeff Bezos, CEO of Amazon, he said, our success at Amazon is a function of how many experiments we do per year, per month, per week, or per day. So that means actually the more experiments they run, the more ideas they can test out. They can know which idea does not work. They can also dig out some valuable ideas which can increase their revenue just with a proportion. So the more experiments they run, the more the positive change ideas they can launch online. And Kevin Scott, CTO of Microsoft, he also mentioned controlled experiments are among the best tools to understand complex phenomena and to solve very challenging problems. And for nowadays, the ability to design controlled experiments and run them at scale is the foundation of how modern high-tech business operate. And coming to the gaming industry, the CEO of Zynga said, we no longer need to build it for 3 months and hope and pray. So basically, previously, without experimentation, we need to build a new feature or new game mode for 3 months. And after launch it, we don't know actually what is the concrete causal impact of this new feature on our users. We need to pray it actually works. With experimentation, we can actually just build a prototype, a very early stage testing version of this new feature, launch it to a small sample size of users, and test their results. If it looks positive, we continue to build this feature out. If it's not a good direction, we can just change direction and save our effort. So by this, we know the quantified impact of this new feature on users. And secondly, we can save our engineering effort for something really important. The King company is a parent company for Candy Crush. So they also run a lot of experiments. They nearly test everything from the game difficulty to promotion offers, just like with the campaigns we mentioned previously. Okay, so hope this can give us some basic idea what actual experiments look like in industry and why we find it valuable to run experiments. So next, let's talk about statistics behind experimentation. So why stats is so important for experiments? Because in school, we learned one important class is the design of experiment. And in industry, the A/B testing is somehow correlated with the class. For example, we studied block design, factorial design. Some of the textbook knowledge is quite useful in industry, and some of them haven't found very direct applications yet. So let's take a look on where we find useful so far. Okay, so why the stats is so important in experimentation? Let's take a look on the previous A/B testing flow. So we first divide users into treatment and control, and then let them to see different versions of the product. And then we make a comparison. We say, oh, actually, the click-through rate in treatment is higher than the click-through rate in control by 1%. Everyone say, oh, let's launch treatment, let's launch version B. But hold on for one moment. So the question is this 1% increase a real causal impact by the version difference or by something else? So that's what how stats comes in. So let's first decompose this 1% difference. This 1% difference is observed difference, which is computed by the treatment mean minus the control mean. However, it's a mixture effect of different three factors. So first, it can be caused by treatment effect. So that's ideal, right? That's expectation of the CTR in treatment minus the CTR, the counterfactuals in control conditions. However, there are some other two factors. The first factor is bias. So there can be a systematic bias caused by traffic splitting. So for example, we split the users randomly. However, maybe there are some bug in the splitting algorithm. There are more heavy users in the treatment than control. Then there's no wonder they can have a higher click-through than control. So there's some already existing bias in the user group. That's possible. Or maybe there's some carryover effect. So probably these two group of users just run another experiment. They have a same splitting rule, and this exact user group just got a really bad experience in the previous experiment, and the other group are probably happier with the previous experiment. Then when it comes to this experiment, they are no longer comparable. These two groups are no longer comparable. One group of users already have a lower engagement. So the measurement of observer difference is actually the mixture of the treatment effect from this experiment plus the previous experiment. So which is not ideal for our experiment here. Another factor comes into the observed difference is noise. So whenever we split users into two groups, they are not identical users. So we will see a difference. So it's really hard to see with split users into the group, the difference is exact zero. They are not going to be exact zero. There must be a difference. It just depends on it's a large difference or small difference. So how to deal with this bias and noise. So because of the one statistic we care about is treatment effect. There's only statistic we care about. We want to eliminate bias and noise. To detect bias, we can use some sample ratio mismatch test. So for example, we split users into 50 and 50, then we can test whether the observed sample size ratio is 1:1. We can use a chi-square test or proportion test to test whether the observed ratio is significantly different from the ratio we design. So it's not necessarily to design the experiment to be 50-50. We can also design for 10% versus 90%, but the observed difference must be consistent with the design difference. There should be no significant difference. Otherwise, it may mean an issue we need to dig in. Another test can help us to detect bias is to run an AA test. So after splitting the user, first don't let them to see two different versions of the product. We just let them to see the same version A. So for both groups, we see version A. We run it for 3 days or 7 days. We test whether there's a significant difference between these two user groups. Ideally, there should be no significant difference because their user experience are the same, except their user groups are different. And if we do see a significant difference between this user group before we render different experience to them, then we need to investigate, maybe there's a systematic difference or a systematic bias. Okay, so that's how we use stats to deal with bias. And assuming after run this quality check, everything looks balanced. Then the task is to eliminate noise. So to eliminate noise, which means we want to tell whether this 1% means there's a real treatment effect or not, we can use statistical hypothesis testing. So that's I assume everyone is familiar with this one. So we just test, given the sample size, the metric variance, whether this 1% is actually is actually significant from 0 or not. And when we talk about hypothesis testing, there are 2 errors we need to pay attention to. The first one is type 1 error, which means there's no actual effect of our treatment, but we do see a statistic difference. And we normally control the false positive rate at 0.05. And for type 2 error, that means there's actual effect, the actual difference between treatment and control, but just due to we don't have enough sample size or our metric is too noisy, the variance is too large, we are not able to see a significant result from a statistical perspective. So both are issues, concerns for us. So we need to find out ways to control our false positive as well as control the false negative. But the first thing to control the false positive is to use the appropriate hypothesis testing method for the corresponding metrics. We are not going to use the same hypothesis testing method for all metrics. Otherwise, it may lead to inflated false positive error. So normally we can divide metric into 4 types. The first type is the proportional metrics. For example, user retention, user conversion. Normally we have let's say we have n users in control and probably 10% of users of these users who are active today are active tomorrow. Then we can calculate user retention as a proportion of a user base. That's called proportional metrics. And each user is independent from each other. And for this type of metric, we use a 2-sample proportion test. And for continuous metric, for example, average time spent per user or number of rounds of games played per user, we use 2-sample t-test. And for ratio metric, for example, click-through rate, this can be very easily mixed with proportion metric. The difference is that the click-through rate is a proportion of impressions have a click, but each impression is not independent because the same user can have multiple impressions and the impressions belong to the same user, they can be correlated. So in this case, if we treat this metric as a proportional metric and use a proportion test, we can easily see an inflated false positive rate by simulation. So in this case, we need to put the correlation within the impressions into consideration. And one method we can use is to use the delta method to do the variance estimation and plug in the variance estimation into the t-test to sample t-test and run the test. And the last type of metric is the quantile metrics. For example, we care about the median of the app load time. So whenever we click an app and when it's fully from opening the app to the front page is fully loaded, so we count the time. And if we have like 10,000 users, we care about the median of the upload time. So for this type of metric, for median, we can no longer use t-test because we don't have the variance for median. And one method we can use is use a bootstrap as a non-parametric method to compare the median in two population or two samples. So how we decide this mapping between metric to the testing method. First, we have some assumptions, and then the most important thing is that we need to run some simulation on real data to test it out. For example, we have all the users' real data, and then we randomly split them into treatment control to run A test, and then we test whether using different methods, whether give us a reasonable false positive rate. We can repeat this splitting for maybe 100,000 times and see whether we can actually accurately control the false positive rate. However, that's a standard method for fixed horizon experiment, which means we start the experiment, we observe the data for 1 week, we collect the data, we analyze for one time. That's very important to analyze the experiment one time and not analyze it multiple times. Otherwise, we are getting a p-value peaking problem because we are doing multiple testing there. However, there's actually a business need to monitor and analyze the experiment continuously and multiple times. How can we deal with this? So if we want to monitor and analyze the experiment continuously, for example, we want to every hour we have the experiment results. The team are eager to know the experiment results because sometimes we launch the experiment, we are worried about there may be some bugs in the experiment, and maybe the designed new version is really bad. Maybe it will decrease the users' engagement by 50%, or maybe some users due to a bug are not able to open the app, not able to place the order. Then that's a serious problem. We need to know this early and stop the experiment early. We cannot allow such an experiment running online for 1 week and then collect the data, find the problem. So the actual need is to monitor the experiment continuously and know the problem early. And then basically we collect the data early like this. So in control, we can count for each hour how many sessions we have for this hour, and we can count the sessions cumulatively for each hour. And then we will count how many sessions contain a purchase event, and then we can calculate the ratio. So we can say, oh, first hour in control, we have 44% of sessions who have a purchase event. The conversion, it indicates the conversion, and in the treatment, this proportion is 53%. And then we can keep counting this hourly data, and then we can plot the percentage of sessions with the purchase event for treatment control. And then we can take a difference. We can see as time goes, we accumulate more data, and the difference should converge to 0. So here we got a basic dashboard for continuous monitoring. However, our statistics haven't come in yet. So we need to run a test to tell us whether the difference is concerning. So for example, we see the first difference is pretty large, whether it actually indicate a very significant difference, then we can probably use a t-test. However, we know t-test is for fixed horizontal test. If we run it one time, it can guarantee our false positive rate is not exceeding alpha, let's say 5%. However, if we do it hourly, for 1 day, we do it 24 times, then it's very likely to see a false positive at least one time. Then if we do a simulation for 1 week, which means we do a t-test for 24 times 7, then we will have 50% of chance seeing at least one false positive if we are running an A test for 1 week. Then basically we cannot use t-test. Otherwise, the experiment team will continue receiving some false alarm. So 50%, half of our experiment will give us some false alarm to say, oh, here's a significant difference, which is actually not true. Then a better method for continuous monitoring is use a sequential method. We can use a sequential probability ratio test, SPRT. So this method, the fundamental idea is based on the likelihood ratio follows a martingale under null hypothesis. And when it comes to confidence interval, we can write the formula like this. So basically treatment mean minus control mean, and then plus minus confidence interval bandwidth, which is a function of the variance of treatment control. We can say in general, the confidence interval is wider than t-test, and then most of case, it will not throw out a false alarm. And if we run it for 1 week, the false positive rate is still around 5%, which is ideal. However, we use the data used for these two pictures is from synthetic data. It's an ideal world. Every data point is independent from each other. And when we put this algorithm into production, we see a problem. We see the actual false positive rate is not 5% on real data, it's 30%. Then we dig into the problem and see where it went wrong. We find out because we are talking about hourly session. So the same user can have multiple hourly sessions because same user can stay with the product probably for multiple hours. The sessions, the observed session unit between different sessions within the same user are correlated. They are not independent. And if we treat them independently, then we will have an issue. So if we assume sessions are independent, we have a 30% false positive rate, which is cannot be tolerated in this scenario. And one approach we use to deal with this situation is to take the correlation into consideration and re-estimate the variance. So basically, we use a delete group jackknife variance estimation. We hash users into different groups. Let's say hash them into 20 groups, and then estimate the variance at a group level. So basically, all the sessions for the same user will be grouped in the same block, and we will honor the correlation among the sessions for the same user and take that into consideration and get the correct variance estimation. And then use this variance, plug into the previous SPRT formula to get the updated confidence interval bound. And then in the end, we are able to get a 5% false positive rate for the real data. We actually also tested different variance estimation methods, including bootstrap, delta method, and jackknife. We can see without variance correction, the false positive rate for the original SPRT is quite inflated on real data. However, if we use this correction method, we can actually control the false positive rate under 5%. However, if we are also consider the engineering from the engineering perspective, the deleted group jackknife actually have the lowest requirement for storage. Delta method and bootstrap require us to store all the hourly session level data in our memory. However, the deleted group jackknife only requires to store the block level information, which is a very small data size. So in the end, we choose delete group jackknife as our in production method. So this is just one story on like how we see business need for continuous monitor the experiment, and then how we design the method, find out the existing method does not work, how we make some correction and make it work in practice. And next, we are going to talk about experimentation system. So from engineering perspective, how does this experiment actually functions? How can we actually split the user and see different experience? So first, let us assume we do have an experiment platform. So to start an experiment, the experimenter maybe is he or she is a product manager or engineer. He will go to the experiment platform and set up an experiment to say, hey, I'm going to split the traffic into 50-50. And for the control group, we are going to show them yellow color of the text. And for the treatment group, we are going to show them a blue color of the text. And then the system will save the data, the experimental data, to say, oh, we have 50-50 split, and the parameter for control treatment are yellow and blue. And then we also have the treatment config to be sent to our backend to say, oh, if we see a yellow, and then send a yellow color font to the user. Otherwise, if we receive a blue parameter, we will just deal with accordingly. So when user comes to the app, this app will send a request to our backend server. And this request will also involve experimentation. SDK will split the user into treatment and control. So randomly using a hash function. And then the backend, after the backend receive the user's request with their experiment group key and say, oh, we receive this user, we need to show a text to this user, and this user is in control. Therefore, we will send a yellow color text to this user. So that's how it actually, the user will see the corresponding, get splitted, and see the corresponding experience from the system. And this is not end of the journey because we still need to collect the data. So user, the app and client side will log the data. So this data will tell us, oh, this user is split into control, and this user also stayed with the app for 10 minutes, or maybe he also made a purchase. All the standard metrics are logged into our data storage. And then after collecting the data, we are going to make a computation and just analyze the results. So there may be some also analysis setup, such as what metrics we care about, which dimension of user we care about. And according to the setup, we make the computation, and then we show the results on a dashboard where the experiment can see. On the dashboard, they can see for different metrics, what is the mean of treatment, what's the mean of control, what's the difference, whether it's significant different from each other. So this is generally how the whole system works for experimentation at tech company. Okay, next we are going to briefly talk about a few other methods in experimentation field beyond A/B testing we found useful in practice. So in general, A/B testing can cover probably 80%, at least 80% of our use cases for experimentation in industry. However, there are also some use cases which cannot be appropriately dealt by A/B testing. So the first example is multi-amp bandits. So whenever we have a lot of treatment groups, let's say we have 100 treatment groups, then it's not suitable to run A/B testing because we cannot just split the 100% users into 100 buckets. That means we are using the whole population to run an experiment, which is very risky because a new feature can mean a user experience degradation. And on the other hand, if we fix the sample size for each treatment variant, we are not able to get enough sample size to get a very accurate estimation for the treatment effect. So multi-amp bandits algorithm are able to make the explore and exploit algorithm, which means we first allocate some small sample size to each treatment group, and based on their performance, we are going to allocate more sample size to the winning group. So which means in the process, we are able to already allocate more traffic to the winning bandit and get more benefit from the winning bandit to give you more users better experience. On the other hand, because we are giving more sample size to the winning bandit, we are able to get a more accurate estimation for the winning bandit. So that's the idea of multi bandits. And next one is uplift modeling. So we will discuss this later. So basically, uplift modeling is very helpful for us to understand the individual level treatment effect or cohort level treatment effect, so that we can treat users differently with their preferred treatment. And the first one is adaptive experiments. So the monitoring part, the continuous monitoring example we discussed is one part of adaptive experiment. And the other part we haven't touched is how to make the automatic decision for ramp up. So let's assume we have one feature which we are very certain we are going to release it to all users, but we just want to run experiment to make sure there's no risk. We want to say we want to ramp up this new feature from 0% to 100%. Then what we will do is probably first we ramp up it to 10%. And the rest of 90% are control experience. And then we ramp up it from 10% to 20%, 50% until 100%. Then in this process, we will continuously monitor how this new feature perform compared to the control experience. At the same time, we also need to make a decision. So according to the observation for this stage, then what is the best timing to ramp up to the next stage, or what is the best sample size we can ramp up to the next stage? So that's an adaptive experiment problem. We need to continuously monitor and also make automatic decision. In the end, we want to make some certain simple experiments as automatic as possible, so that no human need to get involved if there's no issue in the experiment. The next one is interleaving method for ranking algorithm. So sometimes for recommendation algorithm or for search ranking algorithm, some queries are in a long tail. If we just observe the total, if we just split users by users and into treatment control, compare the overall treatment effect, we are not able to get sensitive enough to tell the difference in the long tail queries. And the interleaving is a method to to mix the treatment control experience for the same user, so that we can tell more accurate result for this ranking algorithm experiment. And sometimes we also have some network effect in the experiment. So which means the treatment user and control users are no longer independent and separated from each other. So they may intervene with each other. So for example, we launch a new feature for treatment users, and then this treatment user may, due to this new feature, become more active, and they invite their friends in control, and lead to the control users become more active. So this kind of network effect can either lead to the other group more active or less active than they should be if we separate the treatment control better. So how can we actually separate the users better into treatment control if there's a network effect? So normally we can use probably synthetic control, which means we, instead of splitting at the user level, we split them at the city level. So let's say we have 10 cities, we can assign probably 5 cities into treatment, 5 cities into control. And because there may be some existing bias between those city groups, we can use some regression method to control their past trend of behavior and make them comparable by some modeling method. We instead of splitting at geolocation, we can also split them by time. That's called switchback. So let's say on Monday, we render treatment, on Tuesday, we render control, and next week, we will change, we will just switch the order, and we will make a comparison for treatment control over different times. There's also cluster-based algorithm. So we know, okay, so maybe user will intervene with each other because they are friends. Then maybe we can first plot or find out their friends or social clusters, and then split by clusters, then the cluster, the same friend circle will be all in control or treatment. They will not intervene with the other group. As we can see, these are the ideas to put users into the same group without disturbing the other group of users, either by geolocation, time, or cluster. But whenever we are not splitting at user level, we may see there are some bias because we just split on other bigger unit. So we need to, the splitting is one side, and the other side is we need to use some adjustment method to deal with the remaining bias. And in the end, we are not able to, sometimes we are not able to run a randomized experiment. Another resort for us is to run causal inference based on observational data. One example is use a propensity score related method to deal with this situation. So here is just a few ideas for our audience. If you are interested, you can find out more details for each of the methods. There's a lot of applications in industry already. So next, we want to switch gear and talk about CausalML. So this is an open source Python package for causal learning. I want to introduce the concept of causal learning, the models, as well as this package, so that we can easily get access to these models and apply it in our research or industry applications. So the motivation for me and my colleagues to develop this package at the beginning is to get deeper understanding of our experimentation. So for experimentation, for A/B testing, most of the case we are talking about ATE, the average treatment effect. We compare treatment control, and then we can get their average treatment effect, which means it's a mixture of all users. However, the reality is that not all the users have the same experience, same preference. Maybe we have some users who can benefit from treatment, some users get harmed by treatment, and some users are just natural between treatment and control. And just because there are more users prefer treatment, we may see ATE is positive for treatment effect. But it does not mean every user is actually happy about treatment. So to get deeper understanding of the treatment effect on each individual user, ideally we want to know the individual level treatment effect, which means if we put this user into treatment control, what's their difference? However, for each user, we can only put them into treatment or control in most of cases. And that means we need to come up with the counterfactuals for this user. If we put them into different conditions, what will be the potential outcome and what is the treatment effect for this user. And most of the time, for modeling purpose, we will just estimate individual treatment effect as CAT, the conditional average treatment effect. So the idea here is we will describe different users by their user features X. So this X can be their previous engagement with our product, or can be some other information just to describe this user. And then we will calculate the conditional treatment effect, which is a conditional expectation of the outcome under treatment and this feature condition minus the potential outcome under control and this condition. Therefore, we can see for different users, we may see a different CATE. And by understanding the CATE, we are able to see the user preference over different treatment, and therefore we have better insights, and we can also personalize the treatment. But how can we get the CATE? We are going to use some causal learning algorithm to estimate the first function and second function, and then estimate the difference here. So what is CausalML? So CausalML is an open source Python package for causal learning. A little background about CausalML. So we just decompose the different words. So first we talk about what is causal learning. So causal learning is probably a word getting more popular in recent years. That's a kind of area combining causal inference and machine learning. So these two fields are correlated in this manner. So they are quite a few different business scenarios. We use machine learning to solve the business problem. But we found out if we introduce a causal inference idea into such problems, we can actually find a better solution. So that's why causal inference can help machine learning to deal with some conventional use cases. On the other side, in causal inference, normally we can use some linear regression or some other method to estimate propensity score. And if we use machine learning, which mostly have less constraint on the assumption and more accurate prediction power, sometimes it can enhance the estimation in causal inference. So these two fields can be beneficial for each other, and some methods are a mix of these two. And we are interested in this type of algorithm to help us to solve some business use cases. And then we found out there are some existing papers talking about this method, for example, aptitude modeling. However, there's no Python package for us to use because Python is one popular programming language for data scientists and machine learning engineers in industry, and many of our production systems can be quite friendly to Python, but we don't have good tools back to 2017 and 2018. Then we just decided to develop a Python, some Python methods, implementing some existing method from literature into a package. Firstly, this is only for internal project use at Uber, and then multiple teams found this package quite useful, and it became an internal open source package that multiple teams contribute to this idea. And in the end, we released to public on GitHub, and nowadays this package has been downloaded for more than 700,000 times, and we also received nearly 3,000 stars. So for this package, our goal is to provide one-stop shop of machine learning for causal inference. So we have a dedicated support, which means the open source team right now still meet regularly and discuss the maintenance and upgrade ideas for this package. And also we make it easy to use because we know many of our data scientists are familiar with scikit-learn. So we also follow the standardized scikit-learn library interface. The input and output are quite similar, the format quite similar with scikit-learn, and many interfaces are very friendly to plug in scikit-learn models. And also because this package was originated for dealing with industrial level use cases, we need to handle a large volume of data and with a reasonable speed. This package is designed to able to handle a large data set. As one-stop shop, definitely we need to have many tools in this package. So on one dimension, we have multiple models implemented in this package for solving the same problem. So in practice, we can make an empirical comparison across different models. On the other hand, we also provide some utility tools for us to diagnose or interpret or visualize the model output. So ideally, we want the user to use the same package to complete their project. And getting into this package, what modules does this package contain? So here are the modules, including data generation function for synthetic data, feature selection, different core models for aptitude modeling and causal inference, inference modules, optimization, and model validation, as well as visualization. So first, let's talk about the core models. The core models, the original set are aptitude models, including aptitude trees and meta-learners. And later, we also expanded to some neural networks method and instrumental variables for observational data, observational causal inference. So let's first talk about meta-learners. So remember our motivation for causal learning is to, one motivation is to understand the CATE, which is defined as a conditional treatment effect. we basically want to estimate this formula. And then one simple idea is to construct the estimation for the first component, and then have a different function estimation for the second component, and then we just make a first one minus second one, we'll get the CAT. And this is the idea of SLearner. So for SLearner, we will train a model. This model, the y variable will be the output, and then we will put user features as the input features. But different from the standard models, we will have one additional feature as the input, which is an indicator for treatment and control. So for each user observation, we will have this user is from control or treatment from an experiment, and what's their user features. We feed into this model, we train the model, and then when we make a prediction for the potential outcome for this user under treatment, we just switch the trained model's input for the treatment control indicator into treatment. And everything keeps the same for the user. We get a prediction under treatment, and for the control prediction, we switch this feature input into control and get the control estimation. And then we use the first item minus the second item to get the CAT estimation. So we can see in this method, we use any conventional prediction model can be used as a model here. It can be a logistic regression, can be a random forest, gradient boosting, neural networks. Any conventional model can be used here. That's why we call it meta-learner. We just use conventional models and construct it in a way so that it can serve the purpose for estimating CAT. A little bit more complex model compared to SLearner. SLearner stands for single learner. We can see there's a single model here. The T-learner stands for two model approach, T for two. So in this case, for treatment data, we will train a treatment model, and for control data, we will train a control model. And then we will use a treatment model to predict the potential outcome under treatment, and the control model to predict the counterfactuals under control, and then we can get the CAT estimation. So XLearner and RLearner just a more complex combination of different models, but the nature of those older models are just leverage some existing conventional model and structure them in a way that we can estimate the CATE. And another category of aptitude modeling is use aptitude trees. So the difference from previous one is that the previous one can just use off-shelf models and reconstruct them in a way you can serve the purpose. But for aptitude trees, we need to get into the algorithm itself and change the loss function for each tree splitting. So for conventional classification tree, the goal is to predict the, let's say, the conversion rate for each user, predict the Y itself. And the loss function for each tree split is try to maximize the divergence between different nodes in terms of the conversion rate. So we'd better have a low conversion rate on left node and a high conversion rate in right node. The larger difference is, the better. However, in aptitude trees, we actually, for aptitude modeling purpose, we don't care about the outcome itself. We care about the treatment, which means the difference between the outcome in control and the treatment. So in each tree split, we need to maximize the treatment effect estimation, which means we need to maximize the heterogeneous treatment effect. So ideally, the left node and right node should have a very large difference in terms of treatment effect. So for example, the left node have a very small treatment effect, the right node have a very large treatment effect. That's good. So in the end, we are able to estimate the user's individual treatment effect by seeing which node it gets into and then get the CAT estimation.
Zhenyu, sorry to be a little bit rude because the talk is basically like a 1 hour and we have quite a few questions from the audience. Is it possible that you can like wrap up in like about the next 2-3 minutes? Is it? Sorry.
Oh, yeah, sure,
we
no
have
problem.
some questions for you, you know, quite a few here.
Okay, yeah, let me try that. Yeah, so we also have some in-house development for CausalML. So we have one paper accepted to AI 2022 for feature selections for aptitude modeling, which is different problem for conventional feature selection. And we also have a paper on, when we deal with multiple treatments with different costs, how we can run this value optimization. Such methods are also implemented in our package. For visualization, we have the tree visualization to help us understand what the applicable tree does at each step, can help us diagnose or interpret the heterogeneous treatment effect in the tree, and also have some evaluation visualization on the curve to compare different model performance. The package is designed very simple to use. As we can see here, we import the package and then we generate synthetic data by 2 lines, and then define the estimator and then train and predict the estimator. That's it. So very simple to use. You can try it out. And this package, the method causal learning, can be applied for multiple purposes, such as targeting, personalization, observational study. The idea is that as long as we know the individual level of treatment effect, we can do a lot of things. So we can, just use for ads targeting, call center targeting, email targeting, and also we can personalize user experience based on their personal taste. There's also one observational study where we cannot run experiment at the beginning. We just use some methods in CausalML, such as propensity score methods, meta-learner, and sensitivity analysis to evaluate the model's robustness to finish this study. In the end, I just want to give a big shout out to the open source community. This is not a one person's effort. It actually involves a lot of effort from Uber's data science community as well as GitHub's open source community. So if you are interested in exploring this package, welcome to use this package and share stories or use cases with us, or you can directly contribute to this package if you see some method worth implementing in this package. I think that's it for my presentation. And now let's take some questions.
Thank you very much, Zhenyu, for the nice talk. Now I get the idea why I spend so much time on all different of these electronic platforms and so on. There's like real science involved in. So we have several questions, and for those who want to ask a question, just type a Q in the chat box, and then I'll allow you to speak, and then you can talk directly, okay? Or you can raise your hand. Okay, so I think the first question, let's see, is from Sigurd. I'm sorry if I mispronounce your name. Please go ahead. So let me see. The question here is, have you considered autoregressive moving average, the ALMA model, to adjust for serial correlation in your observed time series?
Okay, so I think I would assume, correct me if I'm wrong, I would assume that is probably for the continuous monitoring problem, right? Let me see here. If this is for the continuous experimentation, then basically in this scenario, we still assume the treatment effect is constant. However, the change we observe here is due to at the beginning we have a small sample size. So we see a quite noisy difference, but the coming interval still covers 0. Over time, it gets stabilized. If there is a treatment effect which can change over time, definitely that's a very interesting topic. Is related to either continuous monitoring or the heterogeneous treatment effect with respect to time. I believe there's probably a couple of papers or industry framework to deal with the treatment effect difference over time. But right now we don't have direct. I don't have a direct study or experience with that. That's one potential research area for different treatment effect over time. And
there's another question that a R package of the CausalML algorithm. Your package is in Python, right? And then probably there's a R community.
Oh, okay. Yeah. So actually, back to like 3 years ago when I first did some research in this area, there was indeed some R package for uplift modeling. I also encourage the audience to try it out. I forgot the name, probably called Uplift or something. It already implement some uplift tree and uplift forest, random forest in R. So basically, that can be solutions in R. But according to my, so the reason we develop Python is mainly because our entire engineering framework is more friendly to Python. And also, we also want to compare different methods, including different uplift trees, random forest, meta learners. So we need one place to put everything together. But there are already some existing R package in R as well.
Yes. Okay. So audience, you can simply talk, I think, if you have a question. Aaron, I think you are the next turn.
Yeah, I had a quick question. When you're sharing your results, especially on heterogeneous treatment effects with your product managers or stakeholders, how concerned are they in understanding that heterogeneity? For instance, are they gravitating more towards a model based on an uplift tree where they can look at the nodes and how they're partitioned, or are they okay with feature importance metrics from a neural network? It's a little more ambiguous.
Yeah, that's a good question. So how we render the outcome of heterogeneous treatment effect to our product team, which assuming to be non-technical team and actually makes a decision. I think the uplift models have two application channels. One is through insights. The other one is through optimization. For insights, normally we even a very basic version of heterogeneous treatment effect is just a dimensional analysis or segment analysis. After observing the overall average treatment effect, we just divide user into maybe new user, old user, maybe divide them into a New York user, Chicago user. It's a very simple dimension division, or maybe it's a 2 dimension together, right? And we can see the different response by users. So that's one standard function on experimentation analysis algorithm. So user can just slice and dice user by different dimension, observe the heterogeneous treatment effect. So that can be pretty easily understandable by different audience. And the other channel for like uplift trees or neural network, we can see it's more complex, right? So we have a lot of machine learnings. In this case, we normally don't communicate the basic logic about the uplift model itself, but we will treat it as an optimization problem. So we say, okay, so now we spend probably a campaign, we spend $10,000 and send this ad to everyone, and we can see probably 1% increase in our treatment, just sending ads to everyone versus not sending the ads to everyone. And then now we have a model. This model can be a black box to the product team. We use this uplift model, and then we are able to target the appropriate audience who are sensitive to the ads and ignore others. By this accurate targeting, we are able to probably with $10,000, we can achieve 2% uplift. We can basically simply state what we are doing and hide the details of the technical above, and then show them a proving experiment, which is the second stage of experiment, just show we can achieve much better business impact to these users. Not sure whether this answers your question.
Oh, it sounds very familiar to what I've heard. Thank you.
Yeah.
Jing Hao, do you have a question? Jiang Tao, I'm sorry.
Yeah, I see. I see Jiang Tao's question in the chat box. So basically, in our continuous sequential testing, we see actually the false positive rate is not the same for different variance estimation methods. That's actually true. So why we see the bootstrap and delta methods are much lower, have a much lower false positive compared to jackknife. The reason is actually the bootstrap and delta method is slightly better than jackknife. The reason because for sequential testing, the claim for this method is that if we test, continue to test for infinite time, it will control the false positive for 5%. However, in this simulation, we tested for 24 times 7 times, so which is above 100 times, but it's still a finite number of tests. So ideally, this algorithm, the false positive rate should be below 5%. If we increase the number of tests, it will be higher and be controlled at under 5%. However, for jackknife, we use a delete a group jackknife. We divide user into 20 groups. That's actually relatively rough estimation compared to delta bootstrap dealing with user level data. So we can see they are getting closer to 5%. So if we double, triple, or 10 times the number of tests, there's a risk the jackknife will exceed 5%. However, in our application, most of our experiment will just run for 1 week for this type of experiment. So that's okay, we use jackknife. But indeed, these two methods actually is slightly better than jackknife from the accuracy perspective.
Okay, and in the Q&A, there's a question, will the deck be shared?
Yeah, I can share a version of the deck afterwards.
Okay, and is there any other question? Okay, has been this recorded? Yes, it is. Yeah, we will post that in the ASA SLDS website, like upcoming events. It has not only the upcoming, but also has an archive of all the previous events and webinars. Other question? And okay, so if you have any other questions, I think Zhenyu left an email, and then you can ask about like the talk itself, the package, or Tencent itself, and about and to contact Zhenyu. Okay, yeah. So yeah, let's stop here. Thank you very much, and let's thank Zhenyu again. Thanks for the great talk.
Yeah, thank you for having me.